welcome to the second lecture of this first module. In the last module, we have talked about the models of various power system components. We have discussed about the models of generators followed by transmission lines as well as the transformers. We are almost at the end of our modeling approach, but before we end this, we need to essentially discuss one or two minor points. So, let us go. Now, we have to talk about load model. Now, we know that loads can be of three types. One is constant power, one is constant current, and third is constant impedance. Constant power load means that if I have a bus, let us say bus I, and some constant power load is connected, we say that it is taking P plus j q, that is taking some constant value of P and constant value of Q. It means that irrespective of the voltage at this bus, this load will adjust the current drawn by it such that this value of P and Q would remain constant. That means, if this voltage magnitude increases, so then in that case this load will adjust itself in such a way that it draws less amount of current, so that P and Q remain constant. On the other hand, if this voltage at bus I decreases, so then in that case this load will adjust its internal impedance in such a way that it draws a higher amount of current, so as to make this P and Q constant. So, it is basically non-linear in nature. In the case of constant current, it is very simple, that if I have bus I and if I have a load connected to it, we say that it is drawing some I current, it is drawing some I current, this is V I. So, then therefore, in this case also, if this voltage increases, so in that case this load also increases its impedance in such a way that the current drawn by it remains constant. Similarly, if this voltage decreases, so in that case this load also reduces its own internal impedance such that this current remains constant. So, it is also kind of a variable impedance load, and the constant impedance is the easiest to understand. So, this is constant power so this is constant current, and constant impedance is the simple to understand, it is just an constant impedance Z, this impedance is Z, this is bus I, this is V I, constant So, then therefore, in this case if this V I increases, so then obviously current drawn by the load also increases, and if this voltage decreases, so then the current drawn by the load also reduces. Now, out of these three, we usually, or rather we generally use constant power loads for our analysis, because the results given by constant power loads are the most pessimistic in nature. So, then therefore, if we are able to ensure that the performance of our system is within acceptable bounds while considering the loads to be constant power only. So, then in that case we would be able to ensure that for all practical loads also the performance of the system will always remain within the specified bounds. In actual reality, no load is either pure constant power or constant impedance or constant current. Every load is actually in some fashion some combination of these three basic types. But for our analysis, as we have just now mentioned, we would be considering all loads to be constant power, because it gives the most pessimistic results. Pessimistic means that if this voltage is reduced, so then for constant power load this voltage would be reduced maximum, and also if this voltage is increased, so then therefore for constant power loads this voltage would be increased maximum. So then therefore if we are able to ensure that my voltage etc. are within limits while considering all loads to be constant power, so then we would be able to make sure that for all other types of loads, that is constant current or constant impedance, these voltages also would be remaining within their bounds. And of course, for all practical types of loads in which these loads are nothing but the combination of these three basic types, obviously these voltages will remain within the bounds. Now, before we proceed further, one simple concept need to be probably recollected. If you remember, in the last module we have defined that this complex power SI is given by VI into II star. Now, the question is that why are we taking the complex conjugate of II only? That is, after all, this VI and II both are complex quantity. So then therefore, between these two there can be 4 different combinations to express VI. One could be VI into II. Remember, dimensionally this is also denoting complex power. This is the first option, option 1. Second option is VI star into II. This is option 2. Third option is VI into II star, option 3, and the fourth option is VI star into II star. Please note, all these 4 combinations dimensionally denote complex power. All these 4 combinations are nothing but the product of voltage and current, which dimensionally denote power. But out of these 4, we only choose option 3. What is the reason? Why don't we choose option 1, 2 and 4? We need to little bit recollect it, or rather understand it, because this is the central expression which we would be using throughout the course. In fact, for any power system analysis, this is the starting point of defining the complex power, that SI is equal to V into I star. So, we need to understand a little more detail why we take V into I star. Now, this is basically due to the convention we take. This has per se does not have anything to do with any technical reason, but it is actually due to some convention. Now, what is meant by that? By convention, in power system analysis, by convention we say, or rather we consider that all inductive loads, or rather the power drawn by an inductive load considered to be an positive. So, what does it mean? So, let us say that I do have an bus I which has got a voltage Vi, and in that bus I there is one load connected which is a combination of series R and L. So, then therefore, if the current drawn by this current is II, so then therefore, this II will lag this voltage Vi by some angle depending upon the value of this R and X. So, this is resistance, this is reactance. So, depending upon the value of R and X, the magnitude as well as the angle of II will change. So, if I take that Vi to be the reference quantity, so then this we take Vi angle 0, and II would be lagging. So, II would be given by magnitude angle minus theta. So, it will have II cos theta minus j II sin theta. So, now if we compute the power SI drawn by the load, and if I do VI into II, so what we will get? We will get VI angle 0 is nothing but VI. So, it is VI into II cos theta minus j II sin theta. Remember, here this j is nothing but the complex operator. So, it is VI into II cos theta minus j VI into II sin theta, and if I say denote that it is P plus jq, that is if I say that SI, that is PI, I stands for. So, if I say that SI is given by Pi plus jqi, after all it is in complex quantity. So, then therefore, from this identity we get Pi is equal to VI II cos theta and Qi is equal to minus VI II sin theta. So, we can see if we take only II, so then Qi becomes a negative quantity, which is in contrast to our convention, because our convention says that for an inductive load, here our load is inductive because it is nothing but R and X. So, for an inductive load, the reactive power drawn by an inductive load should be considered to be positive, but here if we do not do anything, if we just go by this simple principle, we end up in getting the expression of Q, that is the reactive power drawn by the load, which is nothing but the negative. So, it is going against our convention. So, we have to do something to make this positive. To make it positive, we now define SI is equal to VI into II star complex conjugate. So, if I do that, so we can easily see that it will simply reduce to II cos theta plus j II sin theta. So, it is now VI II cos theta plus j VI II sin theta. So, then therefore, this is P plus jq. So, P remains same and Q now becomes VI II sin theta, which is now positive and which is in tune with the convention. So, this is due to this reason, to honor the convention, we take this complex conjugate of the current to define complex power. Okay. Now, so now we are done with the modeling of the individual components. Now, let us see, just take a very simple example, that how these individual models are connected together to form a circuit. So, let us take a very simple circuit. So, let us say I do have a generator. This generator is connected at bus 1, then from bus 1 and 2 there is a transformer. This transformer, let us say that this is 1:1. Then from bus 2 and 3 there is one transmission line, let us say this is a medium leg transmission line. Then between bus 3 and 4 there is another transformer, let us say this is this is also 1:1 transformer, and then there is some load C. So, if I draw this equivalent circuit of this, what I will get? So, I have got a source here, this is the source. So, this is bus 1, then I am putting the equivalent circuit of the transformer. So, let us say this is Z, this is transformer T1. So, this is Z T1. Please note that for a nominal tap changing transformer 1:1, the equivalent circuit of any nominal tap changing transformer is nothing but a series impedance only. So, this is bus 1 and 2, and then from bus 2 and 3 there is a medium length transmission line. So, then therefore, we would be representing it by a pi model. So, this is a pi model, bus 3, and these are the so this is nothing but the Z line, and this is the Y shunt line, this is also Y shunt line. Then again between 3 and 4, bus 3 and 4, I do have another transformer. So, because this is also an nominal tap changing transformer, so it will also be represented as and by impedance ZT2, and then I do have a constant power load, let us say constant power load, this is P plus JQ, this is bus 4. So, our simple power system now being reduced to an equivalent circuit. Of course, if this transformer instead of being let us say 1:1, if this transformer is now off nominal tap changing transformer let us say 1:T. So, then instead of this series connection of ZT1, we would have another pi model. So, that is very trivial. So, we are not really discussing it, or rather say if this is 1:T, okay, let us draw it just for the sake of convenience. So, the second case T1 is off nominal, so in that case this would be, so it is YT, and then there would be some shunt branches here, then there will also another shunt branches here, and then of course, so this is bus 1 and this is bus 2, and then we have this line ZL, then we have got YSL, then I have got YSL, so we reach bus 3, then bus 4 is still an 1:1 transformer. So, it is ZT2, bus 4, and then P plus JQ. So, this is YT and this is Y into 1 minus T, and this is Y into T into 1 minus T. So, anyway, we have already discussed this. So, that is how the equivalent circuit of any power system network can be built. So, of course, if there is any power system network which has got 100 machines, 200 transformers, 1000 lines, 5000 loads, etc., we cannot hope to draw its equivalent circuit on pen and paper and then do the analysis. So, we have to devise some algorithm through which we can do this analysis, right. So, for that so to derive that algorithm, or rather to develop that algorithm, we now need to consider a very important concept, or rather it is essentially the central concept of the power system analysis, which is called this injected power, or rather injected. So, what is our objective? Objective is very simple, that we would like to analyze any general power system network involving any number of loads, any number of generators, any number of bus, any number of transformer, any number of lines, And as we could see right now that as the number of components in power system increases, it is just not possible to draw their equivalent circuit on pen and paper. So then therefore, you have to devise some automatic computer based algorithm to do the analysis. Now, for developing any algorithm to do this analysis, the first central concept which is essential is the injected quantity. So, let us understand what is meant by injected quantity. So, when we talk about injected quantity, this injected quantity is defined at a particular bus. So, then therefore, if I have bus let us say I, we talk about injected quantity at bus I. Now, this injected quantity is actually in shunt. That means, there is some quantity, some electrical quantity which is being injected into that bus from shunt. For example, now depending upon the components which is connected at a bus, there can be three cases. Now, suppose I do have a bus I. One case could be that there is a generator connected to it. This is case 1, this is case 1. Case 2 could be that at bus I, there is a load connected to it, but no generator is connected. So, this is case 2. And case 3, sorry, there can be case, there can be 4 cases. Case 3 is that at this bus, both a generator and a load are connected. Remember, when we are talking about a generator and load are connected, essentially they are connected in shunt to the bus, and in case 4, there is nothing connected to this bus in shunt, remember, but this bus can be connected to let us say bus I, let us say bus j here. This bus also can be connected to bus k here, right. This connection is possible, but when we are saying that there is nothing connected at bus I, that means we are saying that there is nothing connected bus I in shunt, neither a generator nor a load. Now, for case 1, what happens if there is a generator? So, that means it is actually supplying current and power. Physically, current and power is actually entering into the bus. So, then therefore, physically if this current and power are entering into the bus, so we say that this in this case this injected power or current is nothing but the power or current supplied by the generator. So, then in this case the injected current I is given by Ig, G stands for the generator, that is the current supplied by the generator, and Pi should be equal to Pg. Pg stands for the real power supplied by the generator. Similarly, Qi, that is the reactive power supplied by the generator, also would be equal to the injected reactive power to the bus, because physically all these are being supplied or injected to the bus. Now, in the second case, when there is a load connected, now physically a load actually draws current or power, both real and reactive power, out of this bus. So, then physically the direction of flow of this current or real power or reactive power is actually away from the bus, they are actually away. But when you are talking about this injected quantity, we define something which is injected, which is going into the bus. So, then therefore, mathematically, if I should change this notation little bit, should say this is IL, L stands for load, PL, L stands for load, QL, L stands for load. So, physically IL, PL and QL, they are moving away from the bus, they are being taken away from the bus. But when you are defining injected quantity, this injected quantity is something which is being injected into the bus. So, then therefore, injected quantity at bus I for a load bus means when there is only a load connected, should be equal to the negative of the current which is being drawn by the load. Similarly, Pi should be equal to negative of this load power, Qi should be negative of this load power. In the third case, when both a generator and load are connected, so this generator is supplying a current of Ig and this load is taking a current of IL. Physically the direction of current of Ig is moving into the bus and physically the direction of current IL is away from the bus. So, then therefore, net amount of current which is being moving into the bus, that is the injected quantity II, would be nothing but Ig minus IL. Similarly, Pi, that is the injected real power to the bus, would be Pg minus PL, Qi would be Qg minus QL. And in the fourth case, when there is a neither load or neither generator connected, so then therefore, there is no shunt quantity. So, then therefore, neither any quantity or electrical quantity being physically injected to it, neither any electrical quantity being physically taken away from it. So, then therefore, there is no injected quantity. So, then therefore, II would be 0, Pi would be 0, Qi would be 0. Remember, again I repeat, these quantities are nothing but which is being injected to the bus in shunt. Now, this expression for bus 3 or rather case 3 is the most general expression. This covers everything. For example, if I have only a generator connected, that is case 1, but not load connected, so then therefore, IL would be 0. So, then therefore, following this expression, if IL is equal to 0, II would be equal to Ig, Pi would be equal to Pg and Qi would be Qg, which is nothing but exactly what we have already understood from the physical interpretation of case 1 when there is only a generator connected. If on the other hand, if in this case if Ig is equal to 0, that is if there is no generator connected at this bus, so then therefore, Ig is 0, Pg is 0, Qg is 0. So, then therefore, from this expression II would be equal to minus IL, Pi would be equal to minus PL, Qi would be equal to minus QL, which is exactly the same expression of case 2, which we have understood or derived from the physical understanding. So, then there, and on the other hand, if there is neither a load nor a generator connected at any bus, so then therefore, both Ig and IL is 0. So, then therefore, II would be 0 minus 0, that is 0, Pi would be Pg minus PL, that is 0 minus 0 would be 0, Qi also would be equal to 0 minus 0, that is 0. So, then therefore, this expression, the third one, is the most general expression, and we define that II. So, then therefore, we define as the injected quantity is nothing but the electrical quantity supplied by the generator minus the electrical quantity or rather the same electrical quantity drawn by the load. So, then therefore, this is nothing but the difference between the generator quantity and the load quantity. Sometimes students make a confusion that now here in this case, if there is a line connected between bus K and I and bus J and I, and if and also power is coming from bus K and I, so then this power is coming here, say power is coming here, and from here also power is coming here. Sometimes some students think that this and these are the injected quantity at bus I. This is absolutely not correct. whenever we are talking about an injected quantity, that injected quantity is basically would be contributed by the shunt connected elements which is connected at the bus, and the shunt connected elements which is connected at this bus is nothing but either generator or load. Now, when we are talking about a load, now suppose for example, if I have a bus and there is no load connected, but let us say that there is a shunt capacitor connected. So, then in that case how would we represent this capacitor current? In that case, the current drawn by this capacitor, if this current is IC, so this C stands for capacitor current. If this current drawn by this capacitor which is moving away from bus I is IC, we say that this injected current at bus I would be equal to minus IC. Remember, this capacitor is connected in shunt with the bus. Similarly, if instead of a capacitor there is an inductor connected at this bus, so and this inductor is drawing a current of IL, so then in that case also II would be equal to minus IL. So, then therefore, the central point which needs to be remembered is that the injected quantity is nothing but the current or power which is being injected to the bus in shunt from the shunt connected elements, not the current or power which is coming to any bus through the transmission line or the transformer. So, in this lecture we have continued with the power system module, we have continued with the modeling of the power system components. We have first looked into the models of the loads, and then we have recollected our concept of the complex power expression, and then subsequently we have discussed about the concept about this injected quantity, which is nothing but a very central concept for the computer aided power system analysis. In fact, if we do understand injected quantity well, this injected quantity will help us to develop our computer based algorithms. We will continue with this module with these lectures. Thank you.